As we finish up chapter 4 this week, we're going to apply derivatives to relationships where there's lots of motion going on and all the variables are changing at the same time. And so speaking of time, we will be introducing time as the dependent variable. And so that gets to a topic of related rates. And so a related rate is a situation where multiple variables are all changing depending on the single variable of time. As time changes, the variables change as well. So we'll work on creating models for that, and then differentiating both sides of that model, remembering the chain rule all the time, and then identifying and interpreting what the solution means. So time is the differential that we will be introducing here. So we're going to see that in Leibniz notation. When we see how a small change in the value of time will impact all of the other variables. And so we measure that with our other variables related to time. So dx dt, how does x change as time changes? Does x increase? Does x decrease? Does x stay constant? dy dt, how does the variable y change if we change the time of the situation? So we can apply that to any multiple single variable. How does the volume change as time changes? How does the area change as time changes? So we're just going to look at four different situations just to kind of get our bearings and remember how this process goes. So let's set the situation up here. We're looking at someone watching a train go by. And the observer who is watching the train is 70 meters south of the intersection. So maybe they're a car waiting for that train to pass. And so they're sitting down here 70 meters south. The train is an eastbound train. Okay, so the train is heading in this direction and it crosses through the intersection, and now the train is on the east side of the intersection. And so our question is, how fast is the train moving after 4 seconds have passed? It's important not to get hung up on numbers right away, but to really focus more on the variables of the situation rather than the numbers. And so I'm going to call O. O is it looks too much like a 0. Let's call it P for the person. Okay, so the person who is sitting right there, and then we'll say X for the distance between these. So we've got the train, the person, and the distance between them. Now this is a right triangle situation, so we'll be using Pythagorean theorem. So you first want to set up some kind of geometric or some kind of expression for this that doesn't use any numbers at all. So we're going to say, all right, well, we know that p squared plus t squared is going to equal x squared. So it's important that you hold off on using any numbers before you differentiate. Then we're going to take the derivative. So the derivative of p squared with respect to time is 2p times the chain rule of dp dt. And then the derivative of the train would be 2t times the chain rule of dt capital over dt. And then 2x divided by, or multiplied by the chain rule of dx dt. Now we've got all of these 2's in there, so we can divide the whole problem by 2, which will clean it up for us. And now we can start plugging in some of the numbers based on the values that we have. So we know the person is 70 meters south of this intersection, so their value of for P is 70. dp dt is how much the person is changing. Well, the person is waiting, they're standing still, and so that value of dp dt in this situation happens to be 0. Now we need a value for t. 4 seconds have passed, and we know that the speed of the train is 60 meters per second. And so the train in those 4 seconds must have traveled 240 meters. And so I can plug that value in. And we know that the train has a speed of 60 meters per second. Now x. X is going to have to take us back to It's not explicitly given in the equation, but we can find it based on just using a simple Pythagorean theorem. So let me move my 70 maybe over to the outside. So we know we've got 70 meters and 240 meters are the leg. And so a quick Pythagorean theorem tells me that the x value is 250. And then finally, dx dt is the rate we're looking for, how fast the train is moving away from the observer, and that's the measurement of x, which is the distance between the observer, the person, and the train. So that's the only thing we have left to find. We know that this 0 eliminates, and so our dx dt is 240 times 60 divided by 250. And that tells us that the train and the distance between it and the person are increasing at 62.5 meters per second. So the moral is when you're setting up these things, you set up a geometric or trigonometric expression first. Avoid using numbers. Take the derivative. After you've taken the derivative, then plug in the values for each either variable or rate that you've been given. So here's a trigonometric example. Here's again a stationary person who is watching a balloon rise into the air. And so we've got a person here, and this balloon is, going upwards in the air, and the person is watching this balloon. They're standing 200 meters away. Okay, but again, I don't want to use that value maybe quite so quickly, so I'm going to just label that as my x value. I'm going to say b is the value of the balloon, and then we're talking about, as the person is looking at that balloon, there's an angle being formed. Now we're not talking about the distance between the person and the balloon. We're talking about the angle formed by the observer and the ground and the balloon. So this is going to be a trigonometric situation, and we're going to use opposite over adjacent, which would be a tangent setup. So in this situation, tangent of theta is the opposite side over the adjacent side. Or we could also say that that is x times tan theta equals b. Now, why would I do that? Well, I'd rather take the derivative of a product than a quotient. That's just my personal preference. I like the product rule better. So now I'm going to take the derivative. So I'm going to have x times secant squared theta times the chain rule of d theta dt, plus the other side of the rest of the product rule, so tangent of theta times dx over dt. And then on the far side, the derivative of b with respect to the changing time. Now I'm ready to plug in any values that I've been given. So we know that x was equal to 200. So that's a value I have right now. I know that I don't have the value of theta yet, but I do know that the value of theta is changing at 10 degrees per minute. So I can substitute 10. I don't have tangent of theta yet either. Other than, and then I've got dx dt, which is the speed of the person. Again, the person is just observing, and they're standing still. So that would be 0. And then dB dt is the rate at which the balloon is changing, which is what I'm going to answer the question with, which is find the speed of the balloon. So again, our 0 is going to knock out part of this. So I've got 2,000 secant squared of theta. And that's going to equal dB dt. Now secant of theta is the reciprocal of cosine. Cosine is the adjacent over the hypotenuse right now. I don't have the hypotenuse, and I don't have enough information to find the hypotenuse because I don't have a specified angle right now, and I don't have the height for the balloon. So this is about as far, so I realized I forgot a 0, as I can take this question, except for the addition of units. And so this balloon is measured in meters because that's the unit of distance that we're given here in the question. And then minute are the units of time I'm given in the question. So you won't always be able to take this all the way if you don't have enough information of the situation, but you can get an expression with the units as best you can. Here's another geometry question that's going to have to do with volume. Now here's a cone, and the cone is upside down. This cone has a depth of 20 inches and a radius of 8 inches. Now that's only when the cone is full, but a property of cones is that the ratio of the height to the radius will always be preserved no matter how full or empty the cone is. And so we do have that set up that the radius to the height will always have the same ratio, and the ratio is 8 to 20, or in reduced terms, 2/5. If I cross multiply that ratio, that would give me 5r equals 2h. And so I could use that relationship really for to help me simplify this question. All right, this cone is filled with water but leaking. And so again, we're going to avoid numbers right away, and we're just going to start with how do you express volume geometrically of a cone. So that would be 1/3 pi r squared h. Now you have to be a little bit savvy here because you have multiple variables, but we do know that the relationship between radius and the height is something that we can work with. The question is going to eventually be about the depth of the water, and so that's the value of h in this situation. Okay, we've got water that's descending out of this cone, and so h is the variable we want to preserve. So we'd really like to substitute for r, and so going back, we know that r by itself would be 2/5 of whatever h is. So that's going to help me in my equation to substitute in for r. R can be replaced with 2/5 of whatever h is, and that has to be squared. So we're looking at 2/15 pi times h cubed. Again, notice I haven't used any of the numbers of the problem except for the preservation of the 8 to 20 ratio. Now I'm going to introduce time by taking my derivative, so dv dt. I'll have 3 times 2/15 pi h squared times dh dt. The 3 over 2/15 can be reduced, and I'm left with 2/5. Now I can plug in the numbers. dv dt represents the changing value of the volume with respect to time, and we were given that to be 3 cubic inches per hour, but it's leaking, and so that would be a -3 value. Equals 2/5 of pi times h. Well, we don't have h. What we were given is we were given the radius of the water reduced to 3. Well, we can work with that, even though that didn't give us h explicitly. We know that r is always equal to 2/5 of h, and so conversely, 5/2 of r would always be equal to h. And so if the water has a radius of 3 inches, the height must be 5/2 times that, which would be 15/2. Quantity squared times dh over dt. And now it just becomes a matter of, doing the algebra to solve this. So we'll multiply everything by 5. That'll give me -15. I'm going to divide by 2 pi. And I'm going to multiply by the reciprocal, 2 over 15 quantity squared. And that would give me what's left of dH dt. So I'm just going to clean that up. I can reduce, so I'll have negative 2 over 15 pi as I reduce, and that will be my value in dH dt. Now let's get some units on there. So it should make sense that we got a negative value because the height is decreasing. And this is going to be measured in inches as I'm measuring the height. And the unit of the time is out per hour. And that's the value and the interpretation of that. Okay, it's also leaking or decreasing. The depth is decreasing at negative 2 over 15 pi inches per hour. Okay, last one. Here we have our famous cops and robbers problem. So a police cruiser is approaching a right-angled intersection from the north. So here we have our police officer approaching from the north, which means traveling south, chasing a speeding car that's already turned the corner. So here's our car, and that is traveling east. And then we've got the distance between the two, which we'll call x. So again, because this is a right angle, we can use Pythagorean theorem. So we'll say p squared plus c squared equals x squared. Again, I'm avoiding all the numbers at this point until I'm ready and after I've done my derivative. So 2p dp dt, using the chain rule, plus 2c dc dt should equal 2x dx dt. And I'm going to go back and take out all the 2's just to simplify my math a little bit. Now, no one is standing still in this situation. Everybody's moving. The police car is moving, the car that's speeding away is moving, and the distance between them are moving. Okay, the position of the police car, we read that the police cruiser is 0.8 miles north. So that would be 0.8. We also know that the cruiser is moving at 60 miles per hour. But you also have to take into account the direction. And the police cruiser is moving from the north to the south, which we count as negative velocity. All right, the car that they're chasing, the car is 0.6 miles per hour. So we've got 0.6. dc dt is unknown. That will be actually what we use to answer the question. What is the speed of the car? And the value of x. All right, we're going to need to do some Pythagorean theorem again. If we know that we've got one side that's 0.8 and another side that's 0.6, a quick Pythagorean theorem just tells me that x is 1. So we have the value of 1. And then finally, we know that the radar tells us that the distance between the police officers and the car is increasing at 15 miles per hour. And so we've got a positive value to plug in for dx dt. So this gives us negative 48 plus 0.6 dc dt equals 15. And so we'll add 48 to both sides. So 0.6 times dc dt is 48 plus 15, so 63. And then we solve for dc dt by dividing by 0.6, which gives us 105. And the units on that are miles per hour. And so this car is really speeding in their effort to get away from the police officers at this point. So the police officers are only going 60 miles per hour, but this car chases that they're going 105. The police are really going to have to step on it or call in some backup because otherwise they'll never catch them. All right, so I look forward to seeing how you do working with these in terms of the setup at the beginning, and then applying the rules of derivatives and the chain rule to find the related rates with respect to time, and then plugging in each value down to the final one that you can solve for. Okay, I'll see you guys on Tuesday. I hope you're having a good start to your week.